one of the main importances of black holes is to do with the famous law of physics known as the second law of thermodynamics, which tells us that things get more and more random as time goes on. And where, you may ask, is the greatest entropy in the universe, or the greatest randomness, if you like to call it that? It's in black holes, by an absolutely enormous factor. So when the second law of thermodynamics tells us that the entropy increases, or the randomness increases, where is it all going? Where does that randomness or entropy go? By a huge, huge factor, it goes into black holes. And so to understand the second law of thermodynamics properly, we have to understand about black holes. And I think there's more about this that we are going to learn in the future, with some observations, in fact, of signals in the microwave background, which I think are only just beginning to be appreciated. Perhaps I should stop there.
Great, okay, thanks. First hand that went up was Seth Borenstein from Associated Press. Seth.
Thank you very much. Can you can hear me, right? Okay.
Yeah, perfectly.
So in terms, thank you for doing this. Congratulations, very quickly. But in terms of the black holes, when you first, theorized this work in '64, that was about the sort of run-of-the-mill as opposed to the supermassive black holes. Can you explain why each one is important, and which one is even more difficult to understand?
Well, the theoretical work I did didn't have anything to do with the size of the black hole. It would apply whether they were small, just a few times the mass of the sun, or the massive, extraordinarily large ones we see. I'm not sure if I should use the word see, because you don't actually see the black holes themselves, but the detection of these objects, they're much, much huger than we expected in those early days. But the theoretical work that I did doesn't have anything to do with the size of them. It would apply equally well to these super duper massive black holes, which are believed to be around in current observations.
Thank you.
I'm not sure that was that the answer to your question. I can't remember what.
I guess in a way, I mean, just
yes.
But when you were doing this, was in your mind, was it more the smaller black holes?
No.
I mean,
in fact, thinking about large ones was part of the argument. I remember Charlie Misner, who was a big figure in this early work, an American scientist, Charles Misner, and he was arguing that in a way, the larger ones are much more likely, because you see, if you have a black hole whose mass is a few times the mass of the sun, then the density that you would get in order to produce this black hole is absolutely enormous. And people might argue about the densities and so on. But if you have a much larger black hole, the densities are much smaller. They may be even less than the density of air. And so the arguments that were used at that time, and that I used in particular, were more relevant to very large black holes. It's not that we had reason to believe in them at that time, but the arguments were even more convincing, if you like, because you didn't even have to talk about densities even greater than the density of air. So I think it's the other way around in a sense. We were talking about very big ones, yes. But not that they would necessarily be there as really big ones, but for a theoretical argument, the big ones were easier to handle, if you like.
Thank you.
Good. Thank you. Palab Ghosh from the BBC, please, Palab.
Very quick congratulations. Roger, could you tell me how you heard the news, a bit more about the shower scene?
Yes. Well, it was actually.
How do you feel on being a Nobel Prize winner? And a quick, sneaky second question: how did your work change the argument? Because I understand that it was their existence was hotly contested. How did your work change things and what people thought?
Well, I think we should go back to the original. Well, there was sort of pre-black hole work, like Chandrasekhar's work on the mass of white dwarfs and things like that. But I think the paper which was most relevant in all this, directly relevant, was the work by Oppenheimer and Snyder, which was in 1939, just before the Second World War. And they were considering the collapse of what they called a dust cloud. So you imagine this material, and it's called dust because it doesn't have any pressure, so that when it collapses, there's nothing to stop it. And that's the first thing. And the second idealization of their considerations was that they looked at things that were spherically symmetrical. So it was all exactly spherically symmetrical, and so that all the dust was concentrated right into the center. So that the fact that you got a singularity, an infinite density at the center, was in a way not surprising. And I think many people thought that this was just an idealization that you couldn't really trust. If there was some irregularity or some pressure, which might put the dust up, pressure doesn't actually help, but the main thing was irregularities. You might have a very irregular collapse, and as it collapses, the irregularity increases and increases and increases. So the model becomes less and less relevant. So the argument was, is that picture, as presented by Oppenheimer and Snyder in 1939, is that picture at all realistic? And there was a widespread belief that it was not realistic, largely because of paper by two Russians, Lifshitz and Kalatnikov, and they seemed to have an argument to prove that in the general case, you did not get these singularities, and that you would imagine a collapse, they just swirl around, swish around in a complicated way, and come back out again. And that, I did have a look at their paper, and although I didn't notice the mistake, there was actually a mistake in this paper. It was pointed out, I think, by Belinsky somewhat later, but I didn't know about the mistake. I just didn't think that the kind of reasoning that they were using was likely to be totally persuasive. And so I started to think of this question about gravitational collapse. It was partly stimulated by John Wheeler in Princeton. He had a lot of interest in this very question. And what happens? I mean, is it something that you get singularities, or do you get, when I say singularity, that's a place where the densities and the curvatures go to infinity and you expect the thing goes crazy. And so you expect your physics goes crazy. But is this a general phenomenon, or is this something which is very special to the case that Oppenheimer and Snyder considered? So I sort of started thinking about this in a way that people didn't normally think about questions in general relativity. Usually they write down complicated equations, try and make simplifications in order to solve the equations, maybe put them on a computer. Well, that's what happened later on, more things like that. But those weren't the way I was thinking about it. I was thinking about the geometry of what goes on and how light rays behave, what they do when they start focusing, and can you stop them focusing, and that kind of thing. And I had general arguments which were pure mathematical, topological arguments, not the kind of thing people that were using. And I remember go for walks. I used to live in a house which was just on the border of a forest, sort of park with a forest in it. This was, anyway, I walked in this park, and I would think about these questions as I was walking to work. Well, I wasn't to work, walking to the tube station, basically, and thinking about what it would be like to be in this situation with all this material collapsing around you, and what would happen. And so I used my geometrical insights into trying to produce an argument. I didn't really have an argument at that point. I had the types of reasoning were at my, I had them available to me. And the main thing that happened was I was going to work at where I was at Birkbeck College in London at the time. And I was with a colleague of mine, Ivor Robinson, who was an Englishman, who was actually doing work in theoretical physics, general relativity in Dallas, Texas. At the time, he was in London, and we had a long conversation. And he was a wonderful way with words. He was somebody who just listened to the way he spoke, and he had this amazing way with words. And he was talking to me and talking to me. And then we came to this crossroad, and we had to cross the street. And as we crossed the street, we were looking out for traffic, and so he stopped talking. And then we got to the other end, and he started talking again and talking and talking. And then when he left, I began to think that I had some strange feeling of elation. And I said, why do I feel this feeling of elation? And I tried to think, what? Well, And I have this sort of habit to see, why do I feel this or that? And I thought about, well, what did I have for breakfast? No, it wasn't that, when all the morning and so on. And I worked my way to this occasion when I was talking to Ivor. And when we crossed the street, I had a certain idea. And it was this idea which I later called a trapped surface, which is a characterization of when your collapse had reached a point of no return, roughly speaking, but it didn't depend on symmetry or anything like that. It was this general characterization which could tell you that something has gone funny. And I was then able to, when Ivor left, I was able to go back to my office and sketch out an argument which seemed pretty persuasive to me at the time, that you couldn't avoid the singularities. Now, when I say a singularity, that's not really a black hole. The black hole is what prevents you from seeing the singularity, if you like. It's what the nasty thing in the middle. If you fall into a black hole, then you will pretty well inevitably get squashed into this singularity at the end, and that's the end. But the fact that you had a singularity argued for this presence of what we call a horizon, and that was really the picture of a black hole in a very general setting. So although people like Chandrasekhar earlier than Oppenheimer and Snyder and other people had showed that there were really problems. I mean, Chandrasekhar was looking at white dwarf stars, and he was arguing that if they were too big, they would collapse in on themselves. And the question was, what happens? And he raised this as a real problem. I mean, he didn't give an answer or anything. He just said, we are left speculating on various alternatives. And I don't think the idea of actually a black hole, well, the terminology didn't come until a fair amount later. That was after my paper. John Wheeler, I think, was the person who at least was alleged to have said it first. I think it was quite a term that we use quite often for this collapsed configuration, and the fact that no information could get out, so it would look pretty black. And we now see evidence of this from the photographs that are sent from this distant galaxy. You could see in the center this black thing in the middle, which is, I guess, what you'd expect a black hole to look like.
Thank you, Roger.
Caleb, did you want to ask the second part of your question?
If I may, tell us how you heard about the announcement and how you feel about winning it.
Well, of course, it's a huge honor, and it was a slightly strange occasion in the morning because I got a call from my PA, Petrona Winton, who said she'd got this strange message and she wasn't allowed to talk about it and all that. So it was all deadly secret at that time. And finally, I went and had a shower because I couldn't, I didn't know what would go on. So they called me up. I was afraid, shall they call me up when I actually stark naked? And then I'd have to say, what were you actually doing at the time? It wasn't quite like that. But I suppose there was some expectation that, I don't know, I wasn't expecting for this event to happen. No, I wasn't expecting it at all. But it's a huge honor, and I'm sure it will be a benefit to promoting ideas which I hope people will look at a little more seriously. Ideas about cosmology, which I think, I mean, black holes are important in all sorts of ways, which I think are becoming revealed only relatively recently. Certainly in the formation of matter, galaxies and things are very dependent on the black holes in their centers. But they're also important because they are the reservoir of what you might call of the entropy in the universe. So one of the most important laws of physics we have is this thing called the second law of thermodynamics, which tells us that entropy increases, where entropy is, in very rough terms, a measure of randomness. So it's a sort of pessimistic law, if you like. It says things are getting more and more random as time goes on. But where does that randomness go? Well, when you have gravitating bodies, the randomness goes into them clumping together. And where they clump most is in black holes. And according to this formula due to Bekenstein and Stephen Hawking, one has a very precise formula for the entropy in a black hole. And that entropy is absolutely huge. And for the black holes, as we keep observing bigger and bigger ones, we realize that the amount of entropy in the black holes absolutely swamps everything else. So that's where it goes. And then eventually, according to Stephen Hawking's wonderful theorem about the black hole evaporation, these black holes will disappear by, well, Hawking evaporation. They won't do this for the really, really big ones. You would have to wait for more than a googol years. What's a googol? Not a very scientific term, but it's, imagine 1 followed by 100 zeros. So that's a googol. That's even too short number of years. It's probably
Roger, thank you so much. But let some of the others ask some questions.
okay. Anyway, I'm just trying to say that they're important for the reasons of entropy, and I think they will become more important in our later understanding of what's going on.
Thank you so much.
Thanks, Roger. And I'm impressed that you started that question about a shower and then brought it straight back around to physics again. I'm going to take a question now from Guy Falconbridge, who I think is at Reuters. Guy, is that right?
Apologies, I was unmuting. Congratulations. I wonder if I might ask a stupid question, and apologies if this is a stupid question, but I wonder if you might tell us what the biggest riddle is that you see outstanding on black holes. For someone stupid, if possible, would you be able to explain it in simple terms?
Not stupid at all. I mean, the greatest puzzle is the singularities, because we don't know what to do with them. You see, the black holes shield us from the singularities. You don't have to worry about them, in the sense that as the matter collapses into the middle, the densities get larger and larger, and they just exceed everything you can think of. And we haven't the faintest idea how to describe the physics that goes on in the middle, because the densities and temperatures and goodness knows what are just out of all range. But you see, because the black hole doesn't let anything out, if you like, it doesn't let any information out about what's going on in the middle. And so we can get away with not worrying about it. So that's, if you like, the biggest riddle, is what goes on at the singularities. But you see, we might say, okay, well, it's a riddle, but it's not affecting us directly, so who cares? It might affect us later on well, certainly if we want to understand the laws of physics in a deeper way, we need to understand what goes on at singularities. But that's a highly theoretical question, which doesn't immediately have observational consequences. They could have, I don't know quite how I should treat this question. Have I answered it at this point?
Yes, I think so.
Maybe I should stop here, because I'll go on rambling on something else if I'm not careful.
Thank you very much.
Is that all right, Guy? Thanks.
That's excellent. Thank you very much.
Yes.
Okay, the next one is Alok Jarrett, The Economist, please. Alok.
Yeah. Hello. Congratulations, Dr. Penrose. My question is, you mentioned Stephen Hawking just now, and a lot of your earlier work with singularities was in collaboration with him in the 60s. I just wonder if you could help us understand how some of his work relates to and helped sort of the ideas that you came up with in the 60s too, and then, which has then obviously been awarded today.
Well, the theorem that I referred to earlier was the one about black holes. And this was a very general argument. There were certain assumptions in it that you might like to get rid of. Now, I've first encountered, I should explain that in the movie, I'm supposed to have given a lecture, I suppose, at King's College. I did give a lecture on my theorem about black holes towards the end of 1964, I think in December. And according to the movie, Stephen was sitting in the audience with sparks coming out of his head, getting inspired by this lecture or something. He wasn't there. So I suppose you have to take the movie with a certain amount of salt. But on the other hand, Dennis Sharma, who was a close colleague and friend of mine in Cambridge, my lecture was in London, Dennis asked me to give a repeat talk, which I gave, I think in early 1965, and Stephen was present at that talk. And then I had a private talk with Stephen and with, George Ellis, possibly Brandon Carter, I can't remember, but George Ellis was certainly there. And this was a much deeper conversation where we talked about the details of my arguments and the kinds of things that went on. And then Stephen went away and developed these things, mainly to apply them to cosmology. So it was not the singularity in the black hole, it was, but in the opposite direction in time, where we're looking back at the singularity, which is called the Big Bang, where the curvatures and densities go to infinity, or have been at infinity, if you like, which started off the Big Bang. And so the question was, how general was that expectation? Did changing the geometry in this way or that make a difference to it? So Stephen developed these arguments on his own very greatly. And then we didn't have a huge amount of contact. I was one of his PhD examiners. Again, it was wrong in the film. They had Kip Thorne there as well, which was quite wrong. But Dennis and I were there, that's true. And this theorem of that Stephen had, I think there was more than one theorem he had there. And they were clearly advances in what I'd done. And then later on, when I was at another conference and I had to develop all Stephen's theorems together into one lecture. And I remember working hard into the small hours of the night to do this. And I developed a theorem which encompassed them all. And when I got back to England, I phoned up Stephen and said, look, I got a new theorem which doesn't, he said, I've got one too. And it turned out the same result. So we both found the same thing. And that was a paper we wrote in the Royal Society together. So that was a paper which more or less encompassed the theorems that had gone on before.
Great, thank you. Right, so the next question is from Tom Whipple at the Times, but he's unable to ask it himself, so he's sent it in by email. So let me ask this question. It's actually in two parts. The first one is, can you explain trapped surfaces in a simple way? The second part is, I think it's a lesser known fact about you, Roger, that you invented a tessellating pattern that was used as embossing on toilet roll at one time, and which has become known as Penrose loo roll or something like that, whether that's an official name or not. Tom asks, possibly slightly cheekily, is the monetary award that you've received today more or less than the one you got from Kleenex? I'd like you to answer the one about trapped surfaces. Whether you answer the other one is entirely up to you.
I'll answer the other one and correct it a little bit. But the one about trapped surfaces, I'll try. Let me see if I can do this. It's not so easy. See, if you imagine an ordinary surface in three-dimensional space. So imagine a surface, it could be concave, convex, whichever way around, or it could be a saddle-shaped surface. Now, suppose you imagine a flash of light occurring all along that surface simultaneously. Now, if it's concave, then the concave side, the rays of light will converge, whereas on the other side, they will diverge. Now, if it's convex or concave the other way, then they'll converge this way. And if it's saddle-shaped, some rays will converge, some will diverge, and so on. Now, a trapped surface is one where the rays converge both ways, and the surface is closed up. So it's what's called compact. Now, you can't do this. You can do it in ordinary space. It's a bit hard to see this. You can do it in ordinary space without any black holes or anything for a surface which is sort of goes back and forwards in time. It's a bit hard to explain. You have to think of the intersection of two past light cones, if you know what that means. But it's not hard to see that you can have surfaces which are trapped in this sense locally. So the rays converge on both sides, but it's not closed up. So a trapped surface is one which is not only that the rays from that surface converge on both sides, but this thing is also closed up, compact. Now, this is what you see does happen as you go inside the horizon of a black hole. And you can see that, and if you perturb it a bit, change it, wiggle it around, it's still true. So even though you look at the exact solution, which is called the Schwarzschild solution, which is an exactly symmetrical collapse, and this condition is such that if you wiggle it around a bit, it still holds. So that if there are some irregularities in the collapse, you won't get away from having a trapped surface. And I presented arguments of collapsing also. This was in relation to a previous question that we were looking at many, many stars coming together. And you could see much more easily that this trapped surface would occur if you had quite a lot of stars coming together within the size of the solar system. You quite easily get trapped surfaces. And so this would lead to the theorem that you get singularities and therefore a black hole. So that was one question. If I can move away from the toilet roll itself, which is a sort of, I don't know why that catches people's attention, except it's a rather stupid thing. But when we moved into a house that we had just bought, my wife noticed that on the toilet roll there was this pattern. I should explain that the pattern is used in many more serious ways. I should point out most particularly to the Salesforce, I think it's called. There's a huge pattern of these diamond shapes, non-periodic patterns on the Salesforce. It's a trans bay, it's a bus terminal. It's meant to be a train terminal when they get some trains going. But it goes for, I think it's about 8 blocks long. And you see this pattern that goes in and out and in and out. It was quite a job to get it, actually to work on this curved surface. And I must hand it to Fred Clark, who was the architect involved, and his team. And after long discussions, we managed to get this to work on that pattern. So if you don't, rather than looking for toilet rolls, I would suggest you look at the Salesforce Transbay Center, or I should say more locally, at the pattern we have in front of our mathematics building here, the Andrew Wiles building in Oxford. And we have what I regard as a very, very nicely done pattern of what are called Penrose tilings. And you don't have to have toilet rolls. I don't know if you'll get the toilet rolls anymore.
Okay, that's great. And Tom,
as regards to the money, I can't remember. It was enough to pay for all the costs. I think that I didn't actually, it wasn't my, it was there was a person who was making puzzles and anyway, let's not go into all that.
No, that's fine.
Didn't make a huge amount of money out of it, no.
So we've had showers and toilet rolls, and we can have other bathroom related questions or not. I'll go to Vicky Ellen at the Mail for whatever you ask about. Vicky.
Hi there, congratulations. It's just a very quick question. It's a long time to wait to get recognised for this finding, and I just wondered if you were worried that time was going to run out, or if you feel this is slightly overdue.
No, you see, let me tell you, I think it's a bad thing if you've got great ambitions to do science or something. It's a bad thing to get a Nobel Prize too early. I know people who got their prizes I would consider too early, and it spoiled their science. So I think if you're going to get a Nobel Prize for science, it's a good thing to get it good and old before you're absolutely clapped out, I suppose. But well, there's still something to do. But don't get it too early. That's my advice to people. No, it was a great honor to get it, and the work certainly went back to something I did in 1964. But then the significance of black holes took a long, long time to become realized. So it's not surprising that and a lot of other things of importance in the way and very much deserved Nobel Prizes were awarded in the meantime. So I think it's great. I have no problems about getting it. And I think I'm just about old enough. I think, I'm only in my 90th year, so I guess that's okay.
And sorry, could I quickly ask if you're pleased that sorry, did you lose me there, or am I still here?
No, we've got you.
I can get you. Yes.
Yeah, are you pleased that black holes actually have captured the public attention? I think most people probably know what they are, and Brian Cox has perhaps played a part in that. But are you pleased that this is no longer just something for the physicists, that it's part of popular science?
Oh yes, no, I think, well, of course they're great science fiction, or not as great science fiction as they could be, because you really see, people use them in a way which I don't like very much, like wormholes, you see. The idea is that maybe instead of finding a singularity in the middle, you find a little tube which connects you to another part of the universe. And that's really, that's far too fanciful. I have to say that in a certain sense, I'm to blame for this, because I wrote an article for the Scientific American quite early on. And in that point, you see, there were some conditions for that, my theorem, which you might like to get away from. One of them was the existence of a non-compact Cauchy surface. And I won't try and explain what that is. But you see, one of the things Stephen Hawking did was to get rid of that condition, which was good. But the necessity for this thing called a non-compact Cauchy surface, well, how do you say that in a popular article? Well, I said it in a way which made it is that you say you don't join up with another part of the universe, you see. And people picked up on this. I think I blame Kip Thorne a little too, but partly my own article. And people, in order to explain what I meant by that, people got the wrong end of the stick. And to say, well, it meant you could perhaps connect to another universe or something like that, which is not what I meant. And I don't believe that you connect to another universe, but sometimes people say it in that way. And of course, in the film, whatever it was, that film there was rather making that kind of image, which was not really what we expect for black holes at all. So I think you can go too far with the science fiction, but they're kind of easy things to make use of. And I think they are important in a way which I hope will come to light soon. They have come to light already, but I don't know how they've been accepted to that extent much. But I think there is evidence for black holes in a completely different way, which I hope will be picked up very much. Anyway, let's stop talking about that now.
No, that's fine, thank you. Is that all right, Vicky?
That's perfect.
Okay, I'm going to go next to, we've got about 15 minutes maybe at the most. So I'm going to go to Jitendra Joshi at AFP, I think. Jitendra? You're still muted.
I can't hear anything, should I?
Yeah, Jitendra, you're muted at your end.
Okay.
Sorry, can you hear me now?
Hello, yes.
Yes, hi, sorry about that. Professor Penrose, you mentioned just a minute ago you didn't think it was a bad thing to have waited until this stage. Is there any sense of regret on your part that the Nobel Committee didn't award anything to Stephen Hawking, in time?
Well, it's always a difficult one because they like to, you see, they're supposed to be for things which are observed, you see, observational evidence. And I think what Stephen regretted was that his prediction of the evaporation of black holes and the radiation from black holes, you see, he hoped that this would be observed there might be very tiny black holes produced in the early universe, and those would go off very early and you might see them. And there was no evidence for this. I was not expecting that myself because I had reason not to believe in very early ones in the universe, but they weren't seen. And so he was disappointed that this evidence was not there. Now, what he would react to with the current observations, you see, I claim that there is observations of Hawking evaporation, but this is not in what I call our current eon. You see, I was almost saying this in my answer to the past question, but let me say it quickly. According to a scheme which I believe in, the Big Bang was not actually the beginning, that there was something before the Big Bang. And what was before the Big Bang was something like what we expect in our remote future. So in our remote future, we will have an exponentially expanding universe. It expands and expands and expands. But then when all mass decays away in one way or another, then you have no way of telling how big that is. And so this crazy scheme of mine, which I believe may well be right, is that remote future becomes the Big Bang of another what I call eon. So our eon, which began with our Big Bang and continues to our remote future, which is this exponential expansion, began with something which was the remote future of a previous eon. Now, in this previous eon, there would have been supermassive black holes evaporating away by Hawking evaporation, and they would produce these points in the sky, which I call Hawking points. So this would be observational evidence, which would be possibly giving Stephen his well-deserved Nobel Prize, because you could observe these in our eon. And I claim that we are seeing them. I have colleagues who wrote a paper which was published just a couple of months ago in the monthly notice of the Royal Astronomical Society, and by Christoph Meisner and Pavel Nurowski and Daniel Land and myself. And we claim that these little points in the sky, which would have spread out to about 8 times the diameter of the moon, you don't see them, they're in the microwave background, but they would be slightly warmed up regions, and these would be the result of the Hawking evaporation of a black hole in the previous eon. So we claim to see these, and there's evidence, pretty good evidence for at least 6 of these points. Pretty not so good evidence for where to find others, but the evidence altogether is extremely strong that these signals are there. So I'm waiting to see whether people will begin to take these a little bit more seriously. Thanks for your question.
Thank you. Thank you. Right, Adrian Cho at Science has got a question next. Adrian.
Hi, can you hear me?
Yes, I can. Thank you.
So first of all, congratulations. One of the things that really impresses me about our current time is that in the past few years even, the study of black holes has become has gone from largely a theoretical study to very explicitly an observational field. And I would just I'm wondering what your thoughts are on that. Did you ever think that there would be things like LIGO and direct gravitational observation of black holes? Did you think that that was something that you would see?
Whether I would live to see it is the question. No, I was expecting that they would be seen. But of course, when that expectation came, I mean, it was quite from way back in I think Joe Weber was looking at possibilities of detecting black holes way back in the late 90s, 50s. But it didn't become a practical thing until as you say, LIGO. There were other projects before, but the LIGO was the first serious one where we would really expect to see black hole collisions. I think the expectation is that eventually you would see them. And the question is whether one would live long enough to see them. I guess that was the question. So that was not so surprising. I think that the sizes of the ones that they do seem to see now was a bit, they're absolutely enormous. Some of them are huge. They gulp down entire galactic clusters. Well, that's the expectation. If you're looking at the remote future, they would be, they wouldn't just gulp down the galaxy, an entire galactic cluster, because there's nowhere else to go. And if you've got long enough in the universe, they'll swallow them up. So, and then you would expect to see these in the scheme I claim, not in our eon, but in the one before. And I claim we are seeing them. But this is still controversial, and I imagine it'll take a while before. It took a while, and it was certainly very interesting to have lived through it all, because in the early days, there was a lot of skepticism. And you could see there were these sort of yearly conferences in astrophysics in Dallas, Texas, I think they usually were. And I used to give lectures on these and on black holes. And there was a lot of skepticism originally, and then you could see the interest creeping up until finally it got to 50%, and then it sort of whooshed over, and people were really taking them seriously. But it took a long time, and it was quite gratifying to see how gradually people were really taking them seriously, and the importance of them, and to see pictures. First of all, seeing pictures of stars going around in our own galaxy, that was amazing to see. And now the photograph of an actual black blob, which is supposed to be a black hole in a distant galaxy. Yeah, very remarkable and gratifying to see that this work is actually being shown to be something real in the universe. Yes.
Thank you.
Thank you. Okay, we're coming up to time soon, so I've just got probably one more question I could take from Dan Cressy at Research Fortnight, and then a couple of very quick things at the end. Dan.
Thanks, Tom. Congratulations, Professor. Can you hear me both?
I can, and
yes.
Thank you very much.
Great.
Yes.
As someone whose works famously had a huge breadth and who's worked at a number of institutions, I wonder what you make of the current British university system and its focus on impact and specialization, and what the government might do to encourage research that can win Nobel Prizes in the future like yours.
Ooh, yes, no, I'm not sure about that. Well, you see, I mean, what I was doing was not anything you would expect to get a Nobel Prize at that time. It was, I was doing pure mathematics. I mean, you don't get Nobel Prizes for pure mathematics. I don't know. I guess I worry about it rather because I think a bit of, I haven't looked into it clearly enough to know what I think are the strengths and weaknesses of where things are going at the moment. But trying to aim to get Nobel Prizes, I don't think is a good thing at all. No, because it's very, I wouldn't say random. That's not the right word, but it's a chancy business. I mean, you could certainly work in some areas or other areas and do just as good work, and nothing would get recognized in that way at all. And certainly what I was thinking about at the time, I mean, as I said, I was doing pure mathematics, or my job at, certainly the one I had when I was at college was meant to be pure mathematics. And so I wouldn't be expected to do anything which would be worthy of getting a Nobel Prize then. But then relativity or general relativity in England was done in pure mathematics departments. It was not done in physics departments until much later. I was interested in the subject just because I was interested in the subject. And I had a lot of interest from my older brother, Oliver, who read me the Mr. Tompkins books at that time, I remember, and things, stimulation from ideas which had nothing to do with universities at all. So I don't know. I just had a lot of, I think when I was at Cambridge, I did my undergraduate work at London, at University College, and then I went to Cambridge as a graduate student, and I went to lots of lectures on different topics, which was important to me. I was supposed to be doing algebraic geometry, but I went to talks by Bondi on general relativity, obviously very important to me, Dirac on quantum mechanics, equally important to me, and a course on mathematical logic, which in a quite different way was very important to me. So those 3 lecture courses were nothing whatsoever to do with my research. And so what do you say? I don't know. I think it's important for people to have freedom to not to be too tied and directly focused on what they're doing. But on the other hand, if you want to dig deeply into a particular area, you have to be very focused in that area. So I have no idea what the answer is to your question.
Which is a brilliant answer. Okay, good. Thanks, Dan. So look, Roger, I promised you that we would wrap up at about 10 to 4, and there's just 1 minute to go. So let me just try and clear up 2 very quick things. We're wondering whether you thought of the film title yet that you think misrepresented your ideas. And when you were talking about it, I wondered if you meant Dune. Seth Borenstein has emailed to say, do you mean Interstellar? Is it either of those?
Interstellar was the one with they did funny things with wormholes and so on. So that's what I didn't like about Interstellar. Far from the bookshelf and the person coming back, that was nonsense. If you're talking about science fiction films, 2001 I thought was absolutely great. I loved that film. There was another one I rather liked. What was that one now? What's it called? I'm feeling bad at remembering names now. Well, there was another film you were referring to, I think, was there?
Well, I mentioned Dune, but only because it had wormholes in it, but we're going back.
The wormholes are, yes, as I said, that's partly my fault, I think, for saying you can maybe do another universe as a way of getting out of the theorem. But at that time, it was the way of getting out of the theorem, but not since the work that Stephen did on this. No, that wouldn't work. And, no good. Sorry.
And then there was one more question, which will be the last of all, from Jonathan Amos at the BBC, who has said, you are known for hating PowerPoint presentations. Are you still using overhead projectors?
I sometimes, now I've got a new scheme where I use a board, which I do here, I pin it up on a chair and I show pictures on this. I still hate PowerPoint, it's true. And when I use it, I do occasionally, it's always a disaster. So I try not to when I can avoid it. But I have used PowerPoint sometimes. Yeah.
Okay, but not a complete convert. Okay, look, we're going to let you go, but can we just check where are you talking to us from? Are you at your home or your office or somewhere else?
No, I'm in my flat. Yes, I'm at home.
You're at your home in Oxford, is that right?
Yes, indeed. Yes.
Yes. Okay. All right, Roger, it's been an absolute pleasure. Thank you for joining us for the last hour. It's been really interesting talking to you, and congratulations from us all. I hope you enjoy the rest of the day.
Thank you very much indeed. Yeah.